Okay, good evening, everybody. Professor Ayorinde welcoming you to another online review session in organic chemistry. This is the last online session I will have with you coming from Washington, D.C. The next time I meet you guys will be when I'm in Abuja, Nigeria. So you are all welcome. In today's session, we are going to review for the exam number 4. This will be the second review for exam number 4 given by Dr. BAKARE. And since most of you are in Dr. BAKARE's class, we are going to use one of his previous exam number 4 in today's session. So therefore, for today's session, we are going to go over problems 2, 3, 8, 9, and 10. And in addition to those problems, we will go over a couple other problems that are not listed in Dr. BAKARE's previous exam number 4. Okay, I notice some of you have joined us already, and those of you who have joined us, I will recognize you as we go along during the course of this session. Okay, so what I want to do now, before we go to problem number 2, I would like to start with what I call a icebreaker problem. In other words, a problem set that I expect most of you to be familiar with. Okay, to do that, let me call on Dominic. Can you read this question for us? Hello, Dominic? Yeah, can you go ahead? Can you go ahead and read this question for us? Okay. Okay, I think Dominic might be having problem with her mic. Valerie, can you read the question for us, if your mic is working? Okay, well, okay, so let me go ahead and read the question for you guys. It seems to me some of you are having problem with your mic. This question says, provide reagents for each of the following transformations. Okay, in the first set of transformation that we have here, we take a look at this alkene molecule right here. From this alkene, we are supposed to go to this tertiary, this secondary alcohol. Can anybody tell me, just send me the response to this through the text window? Can anybody tell me what kind of transformation is taking place here? What exactly is happening here? In problem A, going from the alkene to the secondary alcohol. Okay, what exactly is happening going from this alkene here to this secondary alcohol? What type of reaction is this? What is happening here? Okay, that is hydration. Okay, so this is hydration. Okay, very good. Okay, what kind of hydration is this? Is this a Markovnikov addition of water, because we know that hydration is addition of water to a carbon-carbon double bond. Is this a Markovnikov addition of water or anti-Markovnikov addition of water? Okay, send your response through the chat window, or you could pick up the mic. Okay, excellent. RSL, anti-Markovnikov addition of water. That is correct. Excellent. Anti-Markovnikov addition of water. And what that means is, since we are adding the element of water to this, what that tells us that we are going to add hydrogen to this carbon here, and to this carbon here, we are going to add the hydroxy group. And that is an anti-Markovnikov addition of water. Anti-Markovnikov addition of water. Okay, now if you recall, for anti-Markovnikov addition of water, what that means is we are going to add hydrogen to the carbon of the carbon-carbon double bond that has less number of hydrogen attached to it, and we are going to add the hydroxy group to the carbon that has more hydrogen attached to it. So that is why we're adding hydroxy to here, and to here we're adding hydrogen. Therefore, we obtain this secondary alcohol. Now, the next question is, what reagent do we need to do this? What reagent do we need to do this? Anybody has an idea? What reagent do we need to do this? Markovnikov addition of water to a carbon-carbon double bond. Okay, send me your response through the chat window. Okay. Okay, no, not exactly, not hydronium ion. You're almost correct, but that is not exactly correct. Try again. Keep in mind, it is an anti-Markovnikov addition. Okay, so what reagent do we need to use here? Okay, very good. So we need to use step 1, borane, that is BH3, and then we follow that up with hydrogen peroxide, in basic medium, okay? And this we call boration. So therefore, this is the reagent. This is the reagent that you need to use anytime you want to add water across the carbon-carbon double bond, in which the addition will be anti-Markovnikov addition. So keep that in mind. That is very important. Okay, so now let us go to problem number B, this here. Let us go to B. Now for B, we want to go from a secondary alcohol. Let me take this out of here. We want to go from a secondary alcohol to a secondary alkyl bromide. We want to go from this secondary alcohol to a secondary alkyl bromide. In other words, we are going to replace the hydroxy group with the bromine atom. What reagent do we need to do this? Anybody has? Okay, excellent, excellent. Okay, excellent. PBr3, okay? Dominic said PBr3. That is correct. Very good. Okay, so the answer to this, let us go ahead and, very good. So here we need to use PBr3. That is the reagent you need to use anytime you want to transform a secondary alcohol or a primary alcohol to a secondary alkyl bromide or a primary alkyl bromide. So folks, you need to know your reagents, because knowing your reagent is the beginning of knowing organic chemistry. Okay, very good. Now let us do C. For C, we want to go from a secondary alkyl bromide, which is this one here, to, we want to replace the bromine atom with a methyl group. In other words, we need to form a new carbon-carbon bond right here. Okay, so what reagent do we need to do this? We want to form a new carbon-carbon bond, replacing the bromine atom with a methyl group. Anybody has an idea? What reagent do we need to use for that? Okay, going from a secondary alkyl bromide, which is this molecule here, to this molecule right here. Anybody has an idea? Anybody has an idea? Okay. Okay, Grignard reagent. Grignard reagent. Okay. So here we need to use a Grignard reagent. What type of Grignard reagent do we need here? Let us see. Keep in mind, what do we need to do? We need to form a carbon, replacing the bromine with a methyl. Okay, so therefore, the Grignard reagent must be a dimethyl copper lithium reagent. Okay, folks, you need to know this reagent, because without knowing them, you cannot do organic chemistry. So your Grignard reagent will be this here. Okay, so that is the reagent that you need. This is the Grignard reagent here. That is the reagent that you need to form a new carbon-carbon bond. And what this reagent will do is to use the methyl group. In this case, the methyl group will be acting as a nucleophile from the Grignard reagent, and that methyl nucleophile will displace the bromine atom in this secondary alkyl bromide. Okay, that is what the Grignard reagent will do. It is an SN2 reaction, displacing the bromine atom. The bromine atom becomes a leaving group, and the methyl group, which is acting as a nucleophile, will be displacing the bromine atom in an SN2 reaction. Now, if that is clear to you, give me a happy face. Okay, see. Okay. Okay, very good. So the point is, you need to know this reagent. Without knowing those reagents, you cannot do organic chemistry. So please, you need the first thing you need to do. Most of you will know this is just pure memorization. And when we get to the next set of problems, then we will see how important knowing these reagents will be, because you need to know those reagents before you could do any other problem in organic chemistry. Okay, so we've done C. Now let us do problem D. How about this here? Let me erase all of this. Let me get all of this out of the way. Okay, for D, what are we doing with D? we are going from a ketone, this ketone here, and we are going to form a tertiary alcohol. And in the process, you can see here, we are forming a new carbon-carbon bond. Okay, so therefore, what will be the reagent that we need for D? What reagent do we need for D, for problem D? What reagent do we need for problem D? Okay, send me your answer through the chat window. We are going from a ketone to a tertiary alcohol. A ketone to a tertiary alcohol. Okay, very good. Excellent, excellent. Okay, Dominic said Grignard reagent. That is correct. We are going to use a Grignard reagent. This is a Grignard reaction. So therefore, what kind of Grignard do we need to use? To be this here. We are going to use a methyl, an ethyl magnesium bromide as our Grignard reagent. That would be step 1. And then step 2, you add hydronium ion. Okay? So what you see here, a Grignard reagent will convert a ketone to a tertiary alcohol. This is your tertiary alcohol. A Grignard reagent will convert a ketone into a tertiary alcohol. This is your ketone right here. Okay, very good. How about E? Problem E. Problem E. What are we doing here? What are we doing with problem E? Anybody has an idea what is going on with problem E? And what reagent do we need for this? Okay. Okay, so for this here, what are we doing exactly? Very good. Okay, not exactly correct. I see some of you saying PBr3. PBr3 will convert a secondary alcohol or a primary alcohol to alkyl bromide. In other words, with PBr3, you could replace the hydroxy group of a secondary alcohol or a primary alcohol with bromine atom. However, if you have a tertiary alcohol, you cannot use PBr3 because PBr3 is an SN2 reaction. The process is an SN2 process. So therefore, since we need to convert the tertiary alcohol, in this case this here, to a tertiary alkyl bromide, we need to use a different reagent. I believe one of you gave us the reagent earlier, and that will be this here. HBr, hydrogen bromide. So anytime you have a tertiary alcohol and you want to convert the tertiary alcohol to a tertiary alkyl bromide, the reagent that you need to use is hydrogen bromide. Okay? So you need to know this reagent. Very, very important that you know this reagent. Now, this is the way I look at it before we go to the next question. Now, I keep telling you, you need to know your reagent. For example, most of you know what vocabulary is. Let me take my pen here. Vocabulary. Okay, vocabulary, of course, is a list of words that you have in your brain. You cannot do anything. You cannot write. You cannot write a letter. You cannot write a poem. You cannot do anything at all unless you have a good vocabulary. In other words, the list of words that you have in your memory, in your brain, that determines the level of communication you are able to have with the outside world. In other words, if you want to talk to people, you must have a good vocabulary, which is a list of words. Now, consider that the reagents and reactions, the reagents and their reactions are the vocabulary of organic chemistry. Of organic chemistry. In as much as you memorize all of those words that you use to communicate with others, when you talk to me or when you talk to anybody, you have a list of words in your brain already. You memorize those words. If you don't have those words in your brain, you cannot communicate with anybody. The same thing happens with organic chemistry. Those reagents and what they do constitute the vocabulary of organic chemistry. If you do not memorize them, you cannot do anything in organic chemistry. Okay, having said that, let us go to the next question, just to demonstrate my point. Okay, I don't know how many of you have a working mic. Ayana, if your mic is working, can you read this question for us? Okay. Okay. Anybody's mic is working, just pick up the mic and read the question for us.
Starting with butane and using a Grignard reagent and the ketone in your synthetic design, provide a synthetic scheme for 2-bromo-2-methylbutane.
Excellent. I believe that was Dominic. Thank you. Okay. No, this question says, starting with ethane, this molecule here, and using a Grignard reagent and a ketone, so they have given you some of the substrate or starting material that you could use, and a ketone in your synthetic design, provide a synthetic scheme for 2-bromo-2-methylbutane. Now, unless you know those reactions that we gave you earlier, you cannot do this problem. This is a synthetic problem, okay? And this is what organic chemists do all the time. When you make new drugs, new pharmaceutical drugs, you need to know the reagents that you need to use in order to make those drugs. Okay, so let us approach this problem here. The first thing we need to know is the structure of 2-bromo-2-methylbutane. Let us draw that. You see that is this here. Two bromo, 2-methylbutane. Okay, so the first thing we need to know the nomenclature, the structure of this molecule. That is knowing your nomenclature. And so this is 2-bromo-2-methylbutane. Now, they also tell us that to make this compound, we have to start with ethane. We said we have to start with ethane, which is this here. Okay, so no matter what we do, we have to find a way to start with ethane and obtain this final product here. And they also tell us that we have to use a ketone. Okay, so I need your assistance here for us to do this problem. Let us number the carbon in this molecule. Let us say this is carbon 1, carbon 2, this is carbon 3, this is carbon 4, and this carbon here, let us call this 5. Taking a look at the final product that you have to make, the 2-bromo-2-methylbutane, at this point, this is where you have to begin to use some critical thinking skills, given the fact that you already know your reagents and what they do. Okay, if you take a look at this final product here, can you make an assumption and tell me which of these carbon in this final product will be coming from ethane? Just give me a guess. Give me a good guess. Given the fact that you have to use a Grignard reagent, okay, which of this carbon will be coming from your Grignard reagent? Anybody has an idea? Okay, anybody has an idea? Which of these carbon? 1 and 5. 1 and 5. Okay, well, that's a good guess. That's a good guess, but it is not correct. I will tell you why later. Okay, give me another try. 1 and 2. No, I will tell you that why it is no. 3 and 4, excellent. 3 and 4, exactly. 3 and 4, I would say 3 and 4 will be coming from Grignard reagent. Now, take a look at what we have here. When you have a synthetic problem of this nature, the first thing you want to do what we call a retrosynthesis. Retrosynthesis. In other words, you want to start from the product and go backward to the starting material, taking one reaction at a time. Okay? So let us do that. Let us do that. Keeping in mind that we have to start with ethane, and we also have to use a Grignard reagent, and we also have to use a ketone. Okay, so now the first question I will ask you, I need your assistance here. I need your help to do this. Let me take all of this out. Okay, supposing we want to take one step at a time, to make this tertiary alkyl bromide. You want to take one step at a time to make this tertiary alkyl bromide. What will be the starting material for that reaction, and what will be the reagent? Anybody has an idea? What class of compound? Just tell me whether it is going to be a tertiary alcohol. Excellent. It has to be a tertiary alcohol because we want to make a tertiary alkyl bromide. Okay? So if you want to use a tertiary alcohol, then what reagent do you need to use? Let us assume that, Ayana, that is correct. Let us assume that your tertiary alcohol is this here. Since it is the first step, that one single reaction that will give you the final product. That is what we ask you to give us. Okay, so this is the tertiary alcohol. So what will, exactly, the reagent will be HBr. Now you see what I told you before, you need to know your reagents. Because HBr will convert a tertiary alcohol to a tertiary alkyl bromide. Okay, excellent. Now the next question that I want to ask you is, how then do we make the tertiary alcohol? Give me that one reaction, just a minute here. Give me that one reaction that will give us this tertiary alcohol? Anybody has an idea? Keeping in mind that you have to start with, use a Grignard reagent and a ketone. Keeping in mind that you have to start, use a Grignard reagent and a ketone. So what single reaction are you going to use to make this tertiary alcohol? Anybody has an idea? Grignard reagent with a ketone. Excellent. Great. That is Rachel. Thank you very much. Rachel said we need to react a Grignard reagent with a ketone. Okay, if that is the case, that you are on the right path. So I will assume that our Grignard may be coming from here, since we want to start with ethane anyway, and then also assume that the ketone will be coming from here. Now, if you follow that logic, give me a happy face. If you follow that, okay, very good, very good, okay, very good. Okay, so if that is the case, then we say we want to go one step at a time now. Keep in mind we are doing retrosynthesis, going one step at a time. So we go back, say, okay, say, okay, our ketone, since we say this part will be coming from the ketone, so therefore I will say the ketone will be this here. Step 1. And then step 2, we follow that always hydronium ion. Okay. And then our Grignard, let me use a black pen here for the Grignard. Our Grignard will be this. Okay, that will be our Grignard reagent. Okay, so far so good. Okay, let me do something here so that you could see everything we've done so far. Let me reduce this. What do we have there? Okay. So far, so good. At this point, we have the Grignard. We have this Grignard here. We're reacting the Grignard with the ketone, this ketone here, and then we follow that up with hydronium ion to finish the reaction, and that gives us this tertiary alcohol. So far, so good. Okay? Very good. Now, the next question is, keep in mind, we have to start with, yes, Ayana, go ahead.
Would it be possible for us to have reacted a ketone with a methyl attached to the MgBr?
Excellent, excellent, excellent. So let me finish this and we are going to come back to that. That is possible. There are so many possibilities here. So, okay, so let me finish this and we'll come back to that. Okay? That is what I mean, that you have to think critically. There is not one single answer to this. There are so many different ways in which you can do this. Okay, so at this point, so we have the Grignard here, reacting with the ketone. We follow this up with hydronium ion. We form a tertiary alcohol. Okay, now the next question is, how then do we form the Grignard? How do you form the Grignard? That's the question I have for you now. How do you get this Grignard? Give me that one reaction that will give you the Grignard. Give me that one reaction that will give you the Grignard. That one reaction that will give you the Grignard. How do you form a Grignard reagent? Primary halide with magnesium. Excellent. Good. So therefore, what do you have? You have, who said that? That was Ayana. Okay, very good. So Ayana said we use this here. We use ethyl bromide. okay, react active bromide with magnesium, okay, in ether as solvent, okay. So that gives us the Grignard. That gives us this Grignard here. Okay, we are almost there. We are almost there. Finally, keep in mind we have to start with ethane. How do you then form the, how do you obtain this here? Where do you get this from? How do you get that? How do you get that? Bromoethane, how do you obtain bromoethane? One single reaction that gives you bromoethane. I know you guys know this, that particular reaction. I know you've done it several times already. Give me that one single reaction that will give you bromoethane. Okay, let us see here. Supposing we, okay, let's just go back. We're going back right here. We start with ethane. This is what they told us to start with. Excellent. Okay, I see Ayana said bromine with light. Exactly. You react bromine in the presence of light with ethane. This is what they told us to start with. That will give you ethyl bromide. And then once you obtain your ethyl bromide, you react that with magnesium in ether as solvent, you get your Grignard reagent. And then once you get your Grignard reagent, you react that with a ketone, in this case acetone. This molecule is called acetone. And follow that up with hydronium ion, you get your tertiary alcohol. And once you get your tertiary alcohol, you react that with hydrogen bromide, you get your final product. Now you see here, you cannot do this unless you know those reagents and what they do. So please, before you do anything at all in organic chemistry, make sure you know those reagents, memorize them. Do whatever you can to know them. Okay, I say that, I want to say this again. Those reagents and what they do, they are the vocabulary of organic chemistry. Without having a good vocabulary, you cannot communicate with anybody. You cannot do anything in life. So the same thing applies to organic chemistry and those reagents. Okay, is there any question on this before we move on? Okay, no question. Okay, very good. So let us go to problem number 2. Okay, okay, I know that I've talked with Ayana has read something for us already. If your mic is working and I've not heard your voice today, can you pick up the mic and read this question for us? Yeah, Ayana, go ahead.
Can we, did you say you were going to go back to talking about the other possible way of the ketone?
Yes, thank you. Yeah, that almost escaped me. Where was that? Okay. Oh, now, okay, very good. Thank you, Ayana, for reminding me again. What you told us was, is it possible that you could very well do this? This could come from your Grignard, right? And if that comes from your Grignard, that means that this part will come from your ketone. Okay? So what would that be? Let us see here. Let's do, so therefore. Okay, but the problem, I will answer your question, but the problem with, I will also tell you what the problem with that is. So if you take this ketone here, if you take this ketone here, and you react that with the Grignard, let me use a different color here. step 1, and then step 2, you add your hydronium ion. Of course, you are going to get this. You get that product. So that is the product. So Ayana, you are correct now. But the problem here is, for you to get this product, keep in mind they told you must start with this here. You must start with a 10. Okay? So that is the problem. Yes. Theoretically, yes, you could do this. But based on the question that they gave you, you cannot do that because the Grignard reagent here, the methyl magnesium bromide, you cannot get the methyl magnesium bromide from the starting material. Do you follow that?
Yes, thank you.
Okay, very good. Okay, and so the other possibilities are there, but the point is that you must follow the guidance of the problem, the question that they gave you. In this case, you are restricted to starting with a 10, and that is why we cannot use this particular sequence, even though it is a correct reaction. Okay, so let us go to 2. Okay, if your mic is working and you have not spoken to me today, can you pick up the mic and read this question for us?
Give the structure of the product of the following reaction and outline a mechanism for its formation.
Okay, excellent. That's Zainab. Thank you. Okay, so as Zainab has read for us, it says, give the structure of the product of the following reaction and outline the mechanism for its transformation or for its formation. Okay, so what do we have here? Let me ask you here, I need your assistance here. What class of compound is this? What class of compound is this? Okay, what class of compound is that? Okay, just send it to me through the chat window. What class of compound is that? Okay, that is an ester. Okay, very good. Okay, that is an ester. Okay, Rachel says, Tamara says, okay, all of you say ester. Excellent. So therefore it is an ester. Now, we also know that here we have a Grignard reagent. Okay, so now what question that I want to ask you. When a Grignard reagent reacts with an ester, what class of compound do you get? When a Grignard reagent reacts with an ester, what class of compound do you get? Once again, this is a case of knowing your reagents and what they do. A Grignard reagent reacts with an ester, what class of compound do you get? Okay. You get a tertiary aqua. Excellent. Ayana said tertiary aqua. Very good. That is what you get. You need to know this. Once you know those reactions, you memorize those reactions, organic chemistry is very simple. Okay. So now, we have this ester here, and then we have this Grignard here. So we know we are going to get a tertiary aqua. So let me go to a new page so we can solve this problem. The first thing they want us to do, to give the product. Then the next thing they want us to do, give the reaction mechanism. Okay. Okay, so let us see. I'm going to write this out so everybody can see. So we have this ester here, and then we have this Grignard. 1, 2, 3, 4. Okay, so we have that Grignard reagent. Okay, of course, step 1, and then step 2. We have the hydronium ion. Okay, so this is the product we are going to get. Since you guys already told us that we are going to get a tertiary alcohol, so we have this. One, two, three, 4. 1, 2, 3, 4. So this is the product. This is our tertiary alcohol. Now you see here, what happens here, anytime you have a Grignard reacting with an ester, 2 of the alkyl group that you obtain in the final product, 2 of the alkyl group, this here and this here, come from the ester. Come from the Grignard. In other words, the Grignard will produce the 2 alkyl group of the ester molecule. Okay, so keep that in mind. So therefore, this is the product that they ask us to give. Now the next thing they want us to do is to give the mechanism of this reaction. In other words, how did this happen? Okay? Now, keep in mind that when you have a Grignard reagent, now that we want to do the reaction mechanism, this carbon here that is attached to the magnesium is your nucleophilic carbon. It's your nucleophilic carbon. In other words, that is the carbon that is going to attach itself to an electrophile. And also, therefore, we also know that anytime you have a carbonyl of an ester, a ketone, or an aldehyde, in this case, this carbonyl here, this carbon here becomes your electrophilic carbon. So this carbon becomes your electrophilic carbon. In other words, this is the carbon to which the carbon of the Grignard will attach itself to. Okay, so how does that happen? Anytime you have an electrophile is positively charged, and nucleophile is negatively charged. Okay, so the negatively charged nucleophile will attack the positively charged electrophile, and you form a new carbon-carbon bond. Okay, so now let us give the mechanism for this reaction. Okay, so we start with this. And then we have our Grignard here. I'm going to use a small type to show the Grignard, the magnesium part of the Grignard, because we don't really need that. Okay. Okay. So now what we have this here. Nucleophile comes here, attacks the electrophile. This carbon here of the electrophilic carbon, we only have 4 bonds, so therefore we are going to move the pi electron to oxygen. Notice what I'm doing here. Every time you draw this arrow, you are saying that you are moving a pair of electrons. Okay, so a pair of electrons on the nucleophile attacking this electrophilic carbon here, and then the pi electron on the electrophilic carbon moves to oxygen because oxygen is more electronegative. Okay, so what do we have? So we obtain this intermediate. Now we have the Grignard carbon right here. Okay, so the Grignard has attached itself to that. Of course, we could simply now, just to show that we still have the magnesium somewhere here, let us have the magnesium and bromine here somewhere. Okay? Okay, so now we form this intermediate. This intermediate is very unstable, this here, very unstable. So what it wants to do, it wants to regenerate the carbonyl carbon, or the carbonyl group. Okay, in so doing, if we therefore want to regenerate the carbonyl carbon, or the carbonyl group, we move this pi electron back to here. And we know that carbon can only accommodate 4 bonds at any given time. So something has got to give. The carbon-oxygen bond is not as strong as the carbon-carbon bond. So that will give, that will break, taking away a pair of electrons. Okay? So now what do we have? Okay, let me move this a little further so we can see the next step. So what do we have? We now have okay, so now we have this ketone is formed, and in so doing, we have lost this is gone. The methoxy group is gone right here. Okay, and of course that will be complexing with the magnesium. We don't really need to worry so much about that. Okay, now, so now what we have formed this ketone. What we have formed is this ketone. Now remember the last problem we did? You guys told us that a ketone will react with a Grignard reagent to form a tertiary alcohol. Because ketone is very reactive, so what is going to happen? Once you form this intermediate ketone here, this intermediate ketone will now react with another molecule of a Grignard. Okay, so therefore, what do we have? Let me move this. Okay. Let us have another molecule of the Grignard. One, two, three, 4. So we have another molecule of a Grignard here, acting as a nucleophile. Let's have magnesium and bromine here. Positively charged magnesium. Okay, so now reacting as a nucleophile. Let me take this out of here. Attacking the electrophilic carbon of the carbonyl, pi electron going to oxygen, and then what do we have? Sorry, Should be drawing the arrow backward. This arrow should be going here. Okay. And so what do we have? Let us see. So now we have this. I got too many electrons there. Let me take out one of these here. Okay. And then we have this. One, two, three, four. 1, 2, 3, 4. Okay, so now we form this intermediate alkoxide. Say alkoxide. Okay, of course, you see I have somewhere here, the magnesium is complexing with the negatively charged alkoxide. Okay, so at this point, now the alkoxide, what does it do? Can anybody now tell us, well, at this point, what do we do in the reaction mechanism? Once we form this alkoxide, what is the next step? Anybody has an idea? What do we do next? Exactly. You now add the hydronium ion. So at this point, you are going to get an acid-base reaction. Excellent, excellent. So now you get an acid-base reaction. Okay, so we have this here. Let us use a green color to show our hydronium ion. It's positively charged. It's only a pair of electrons. Okay, so now you are going to get an acid-base reaction in which this alkoxide ion here comes here to pull this proton away from the hydronium ion, and in so doing we are going to release the pair of electrons to oxygen to release water as a molecule, and so therefore what is our product? I want to show the hydrogen is coming from water. Okay, and this is our final product. Okay, so what have we shown you here? We have shown you the mechanism for how we go from an ester to a tertiary alcohol. Let me reduce this so that you see the full reaction mechanism. Okay, what do we have? Let us recap what we've done. We started with an ester. The carbon of the carbonyl of the ester is acting as an electrophilic carbon, and then we have the Grignard reagent. This carbon of the Grignard is acting as a nucleophilic carbon. The nucleophile attacks the electrophilic carbon, and then you form the intermediate, which is this here. The intermediate alkoxide ion. Okay, and that alkoxide ion is very, very unstable. It is capable of reforming a carbonyl, and that is what is done here. Reforms the carbonyl to form a ketone. And we all know that ketone will react very easily with a Grignard. So another molecule of the Grignard now comes in. Okay. Okay, comes in right here. The Grignard will now react with the ketone to now form another alkoxide ion. And this alkoxide ion simply now comes in to remove a proton from the water. So you now form your tertiary alcohol plus, of course, water. So what we've given you here is the reaction mechanism for the transformation of an ester to a tertiary alcohol. Now, let me ask you this. Supposing I gave you a ketone. Supposing I gave you a ketone, and I say I want you to give me the reaction mechanism for the reaction of a ketone with a Grignard reagent to form a tertiary alcohol. What would that look like? What would that look like? Okay, let me number this sequence here. Maybe that might help you to answer that question. Okay, let us call this. Let me erase most of this. It's getting very crowded here. Take this off, take this off, take this off, this off, this. Okay. Let us say this is step 1 of this process that we're giving you here. This is step 1, right? Okay, this here is step 2. This here is step 3. Okay, and this is step 4, where you have the hydronium ion. Now, supposing I gave you a ketone, and I say, give me the reaction mechanism for the transformation of a ketone to a tertiary alcohol using a Grignard reagent. Which of these steps are you going to use? Which of these steps are you going to use? Exactly. 3 and 4. It's just 3 and 4. Just 3 and 4. Okay? Now, supposing I gave you an aldehyde. I give you an aldehyde, and I said an aldehyde will react with a Grignard reagent to form a secondary alcohol. Which one of these steps do you think you will use? Which one of these steps will you use? No, no. Keep in mind, this is an aldehyde. This is an aldehyde. Very similar to a ketone. Okay, the carbonate is attached to difference here. The carbonate is attached to an hydrogen. A Grignard will react with an aldehyde to give a secondary alcohol. So if I tell you that, and I say I want you to give me the mechanism of that reaction, which of these steps will be similar for the mechanism of an aldehyde going to a secondary alcohol reacting with a Grignard? Which of these steps will you use? Which of these steps will you use? 3 and 4, exactly. These are very similar. It's 3 and 4, okay? Because if you have an aldehyde, and I gave you a Grignard, this Grignard here, okay, what is going to happen, this Grignard here, the methyl Grignard, if you use methyl Grignard as an example, if you attack this goes here, and what do you get? Get this. And the methyl group from Grignard is here. And at this point, what do? You just add hydronium ion. And that is your step 4. You add your hydronium ion. So this will be similar to step 3 in the reaction with the ester. This will be similar to step 3. And this will be similar to step 4. Okay? Okay. Anyway, so let us now go to, before we leave, I do want us to do some spectroscopy problem. Have you guys done a spectroscopy already in class? Yes or no? Just give me yes or no. Have you done spectroscopy? Yes or no? Yes, okay, very good. Okay, so let us therefore go to problem number 8. Problem number 8. Okay, I do want anybody who has not talked to us today, can you pick up the mic and read question 8 for us? Anybody?
What is the expected multiplicity for proton resonance indicated in the following molecule?
Okay, excellent. I believe that was Rachel. Okay, very good. Yeah, okay, thank you. Okay, so what this is saying here, just as Rachel has read for us, says, what is the expected multiplicity for proton resonance indicated in the following molecule? I know that you guys have done a spectroscopy already, so but I will give you a little bit of background here. Okay? Okay, let me go to a blank page. There's something we call N+1 rule, particularly when we get to proton NMR spectroscopy, because this particular question has to do with proton NMR spectroscopy. Okay, so there is something we call N+1 rule. And what is that? In order to describe for you what N+1 rule, what it means, I am going to use as an example this molecule. Supposing I have this molecule. This is a ketone. Now, in proton NMR spectroscopy, the signal, if you take a look at these 3 hydrogen here, they are attached to this carbon here. They are attached to this carbon. On the other hand, these 2 hydrogen here, they are attached to this carbon. So let us call this, I will call this carbon 1. Let's call this carbon 1 and carbon 2. Carbon 1 and 2 are joined to each other. They are next to each other. I will say adjacent carbon atom. In other words, next to each other. Now, what the N+1 rule says, the signal for those hydrogens that are attached to carbon number 1 will be split into N+1 peaks. Split into N+1 peaks where N equals to the number of hydrogen that are on an adjacent carbon atom. In other words, N is the number of hydrogen that are next to this hydrogen here. If you take a look at the hydrogen attached to carbon number 2, those hydrogen will be seeing the hydrogen attached to carbon number 1. Okay? Similarly, the hydrogen attached to carbon number 1 will be seeing those two hydrogens attached to carbon number 2. So they see each other. This is what, the technical term we use for this is coupling. But we don't need to go into all of that at this point. So we will say that the hydrogen on carbon 1 and the hydrogen on carbon 2, they are coupling each other. But for your sake, let us keep this very simple. What is simply meaning is that they see each other, and they will split each other into n+1 peak. And therefore, what does that exactly mean? This is what it means. If I look for the signal of this hydrogen on this carbon here, on carbon number 1, those signals will look like this. The signal for this hydrogen here. And then we call this triplet. Triplet because the reason why they are split into triplet, because they only see two hydrogens next to it. Keep in mind the n+1 rule. N is the number of hydrogen that a given set of hydrogen will see. Okay. So based on that logic, if I ask you, what will be the splitting or multiplicity? Actually, we refer to it as multiplicity. We call it multiplicity. If I say, what is the multiplicity of the hydrogen on carbon number 2? We call this carbon number 2. Okay, on the hydrogen attached to carbon number 2. What would be the multiplicity? Anybody has an idea? Quartet, excellent, excellent, because of the n+1 rule. Okay, very good, very good. So you guys got the idea. So we don't need to spend too much time on n+1. You know what n+1 is. So therefore, this hydrogen here will be split into, the multiplicity will look like this. And we call this quartet. Okay? So we say the multiplicity of this is quartet. In other words, the multiplicity tells you what type of hydrogen is next to a given set of hydrogen. Okay? So this is a quartet right here. How about this one here? Can anybody tell me what will be the multiplicity of the hydrogen attached to that carbon? Okay, it doesn't see anything. It sees 0, right? Very good. But 0 plus 1 is what? It's 1. So that becomes a singlet. So this now looks like this. So we call this a singlet. Okay? Okay, so now you guys got the idea. So now let us now go back to question number 8. The question is, what is the multiplicity for proton resonance indicated in the following molecule? Let us number this. Let me put numbers on this so it make it easy for us to interact with each other. Let me call this here, these two hydrogen here, let's call this 1. This here, let us call this hydrogen 2. Let us call this hydrogen 3. Let us call this 4. Let us call this hydrogen here, since we have arrow here, let us call this 5. And let us call this 3, this metal at the end, let us call this 6. Somebody asked a question. I do not understand why the multiplicity on the last carbon because if there are 3 protons on. Okay, let me see here. So you do not understand why the, or in the previous example, let me go back. I will come back to the, somebody's asking a question here. Okay. Okay, the question somebody is asking that they do not understand why this is a quartet. Is that, I'm assuming that's what you're saying. This is a quartet because these 2 hydrogens here, they are seeing 3 hydrogens on the next carbon atom. So the multiplicity is an indication of what is on the next carbon atom, not what is attached to that particular carbon atom. So because these 2 hydrogens are seeing 3 hydrogens here, therefore as a result of the n+1 rule, so the number of peaks will be 4, and that is why you get, this is a quartet right here. In other words, the quartet simply tells you what is next to it. It isn't telling you what is attached to that carbon. Okay? Similarly, if you look at this here, take this out. Okay, if you look at this hydrogen here, the hydrogen on this carbon here, we'll be seeing 2 other hydrogens, and that is why the multiplicity for these 3 hydrogen is a triplet, because the multiplicity is a measure of what they see, not what is attached to that particular carbon. It's a measure of what they see. Okay? Okay, so let us move on. Okay, number 8. Okay, so now let us now do this. Okay, I need your assistance here. For hydrogen, the set of hydrogen that we call 1 on this carbon here, what will be the multiplicity? What will be the multiplicity? For the hydrogens that we call 1, what will be the multiplicity? This here, what will be the multiplicity of these hydrogens? Keep in mind, this hydrogen is attached to this carbon, and this carbon is attached to a carbon that has 2 other exactly. So therefore, the multiplicity of the hydrogen that we call 1 will be triplet. So this will be triplet. Okay? Very good. Now, about 2. This hydrogen here. Take a look at this hydrogen here. Okay, take a look at this hydrogen here. It's attached to this carbon here. But this carbon is also attached to this carbon and this carbon. In other words, the question is, how many hydrogens does this hydrogen see? It sees 4, right? Therefore, the multiplicity will be a quintet, because this hydrogen here is seeing 4 other hydrogens. You have 2 hydrogens here and 2 other hydrogens here. So this hydrogen here that we call hydrogen 2 is seeing 4 other hydrogens. 4 plus 1, that is 5. So therefore, that becomes a quintet. So this becomes a quintet. Okay. About 3, hydrogen 3. What will be the multiplicity of hydrogen 3? Hydrogen 3. Hydrogen 3 is attached to this carbon right here. Okay. How many hydrogen is that hydrogen seeing? How many hydrogen is it seeing? Let us look at it. Let us look very carefully. Okay, this carbon here is attached to this carbon here. It's also attached to this carbon, right? This carbon here has no hydrogen. But this carbon here has one hydrogen. So therefore, how many hydrogen is hydrogen 3 seeing? Exactly, it's seeing 1. So therefore, 1 plus 1 will be a doublet. So therefore, this is therefore, so therefore, this hydrogen 3 will therefore be a doublet. The multiplicity will be doublet. Keep in mind, the multiplicity is a measure of what they see. Keep that in mind. It is a measure of what the set of hydrogen is seeing. So in this case, this hydrogen here is only seeing one other hydrogen, and that is this here. Okay? Because there is no hydrogen on this carbon. Okay. Now let us go to carbon hydrogen 4. Let us go to hydrogen 4. What will be the multiplicity of hydrogen 4? Exactly, it's doublet, because hydrogen 4 only sees one hydrogen on the next carbon atom. Keep in mind, there is no hydrogen on this carbon. There is no hydrogen on this carbon. The only other hydrogen that hydrogen 4 is seeing will be this here. Okay, so therefore it is also a doublet. 1 plus 1 is 2. That is how we get the doublet. Okay, moving right along. About the 2 hydrogen on 5. The 2 hydrogen that we have in 5. What will be the multiplicity? Oh, I'm sorry about that. Let me go back. 8. What happened to my... okay. Let's go back to here. Sorry about that. Okay. Actually, let me just make it smaller so we can see. Okay. About 5, the hydrogen on 5. What will be the multiplicity? Quartet, excellent. Tamara said quartet, Zena said quartet, Rachel said quartet, excellent. Because these 2 hydrogen here, they also see 3 hydrogen on 6. 3 plus 1 is 4. So therefore, the multiplicity of the hydrogen on 5 will be a quartet. That is for this hydrogen here. Okay, this is quartet. Okay, about the hydrogen on 6. About the hydrogen on 6. Right here. What would that be? A triplet. Excellent. You guys are beginning to get the idea now. This hydrogen on 6, that would be a triplet, because these 3 hydrogens here, how many other hydrogen do they see? They only see 2 other hydrogen. 2 plus 1 is 3. So therefore, this is a triplet. So I would advise that you guys should do a little bit more practice on this, because actually this is really very simple. Once you know the rules that you have to follow, really it should be fairly simple to most of you. Okay, now is there any question on this before we do the last question, and then we call it a day, because it's almost 8:30. Any question on this? Okay, by the way, those of you who came in late, I did announce that this will be the last online session that I will be giving for you guys, in which I will be in Washington, D.C. The next time we will meet online, I will be in Nigeria. So I will be sending you an email, let you know what time we should meet to review for your final exam. Okay, just make a note of that. Okay. So if there is no question on this, let us do the last one. And that is 9. Okay, because our time is about gone. We are now at about 8:26. So let us see if we can get out of here by 8:30. Okay. Can somebody read question 9 for us? Anybody? Oh, I didn't hear you. I heard that. Go ahead. Do it again.
Which of the following structures meet the description in each of the 1 through 5 below?
Okay, thank you. Okay, so what this question is asking you, this is also a question on spectroscopy, mostly infrared spectroscopy. It says, which of the following structures meet the description in each of questions 1 to 5 below? Okay, let us look at this. Okay, I also need your help here. The first one says infrared absorption at 3,500 and 2150. Now, this set of questions here, I don't know whether Dr. BAKARE has given you the table of infrared absorption. This table, you find this table in your book, and for any exam that you do, you will be given a table of infrared absorption so that you have an idea what is the range of the absorption frequency for different functional groups in organic chemistry. Okay, so for now, anytime you see a signal at 2150 wave number, what that is telling you is that you have a triple bond. Okay? It could be a triple bond of an alkyne or a triple bond of a nitrile. Okay? Now, but in this particular instance, it also tells you that you have an absorption at 3100. Okay, generally when you have an absorption at 2150, which is due to a triple bond, and then you have absorption at 3300, what that tells you is that you have a terminal alkyne. Because this 3300 here, that is the carbon hydrogen frequency. Okay? So therefore, that tells you you have a terminal alkyne. Okay? So therefore, which one of these structures here will relate to the question I? Which one of the question here will relate to question I? D, exactly. Good. So this is just a question of knowing the absorption frequency for the different functional groups. But just as I told you a few seconds ago, you will be given a table of those absorption frequencies. But it is better for you to actually know them so you don't have to be looking at the table all the time. So the answer to this is D. This one is D, which is this one right here. Okay? Okay, but the next one says strong infrared absorption at 1715. Strong infrared absorption at 1715. You will also note that infrared absorption at 1715 generally will refer to ketones. Okay, will be referred to ketones. So therefore, what will be of all these compounds here? Which one will it be? F. Okay, so this is a fairly simple set of questions indeed. So this will be F. Okay, let me use a different color pen. So that would be this here for F. Okay. Now the 3 says strong infrared absorption at 1710 and a broad absorption between 3400 and 2500. Okay. The key to this is, if you notice here, the 1710 absorption is due to carbonyl. It's also similar to the carbonyl of a ketone. Okay? However, if you look at here, they also tell you that you also have an absorption which is broad at 3400 to 2500. Whenever you have that, what that is telling you is that you have a carboxylic acid. In other words, this tells you you have a carboxylic acid. Okay, the broad absorption at 3400, that is due to the hydrogen, this frequency, the stretching frequency of the oxygen-hydrogen bond, this right here. Okay, and of course the 1710 is due to the frequency of the carbonyl function. So therefore, which one of these compounds would this relate to? C, exactly. So that would be C. Okay, so that would be C. So this is C, and that is this here. Okay, now we have okay. Now we have 4, a strong infrared absorption at 1740. Okay, the key to this is 1740. Generally, whenever you have an absorption somewhere between 1735 to 17. Sorry about that. Let me bring this back up. Between 1735 and 1740, what that tells you is that you have an ester. That is the absorption frequency of the carbonyl of an ester. Okay, so therefore, which one of those compounds would that relate to? Oh, that would be G, exactly. Very good. That would be G. Let me use a different, use a black color here. That is G, which is this one here. Okay, and finally, 5. Strong absorption, infrared absorption at 3400, which is also broad. Okay. Okay, just once again, this is a question of knowing the frequency for different functional groups, of course, which will be in the table of functional groups that you guys will be given. Anytime you see 3400 and it is broad, that means you have an hydroxy group of an alcohol. So that is due to the oxygen-hydrogen stretch of an hydroxy group. And so therefore, what would that relate to? Okay, E. Very good. Okay, I don't have to say E. That is correct. So that is E. Okay? And so therefore. So I think we've come to the end of our session today because we have spent about 90 minutes already. And that is E. Okay, now, is there any question before we leave? Yes, Ayana, go ahead.
Would you be able to email us some of those warm-up problems we did?
Which one is this?
The one.
Oh,
the ones the first.
What? The one we did in this session?
Yeah, the first couple of problems.
Oh, the first couple of problems. Okay, but I will also post the session. I will post this session in YouTube tomorrow, and I will post this in your Blackboard page. Is that okay?
Yeah, thank you. If you have any more, I was wondering if you would.
Well, I do have a lot of problems, but I'm not too sure exactly what Dr. BAKARE has taught you. So that's why I really do not want to give you too much. But okay, what I will do, I will email you my own exam number. Actually, because our exams are different. I tell you, I will email you my exam number 3, okay? And then just play around with it. And also email you my exam number 4. Okay, just play around with it. And then if you have any problem, you could email me because I will be traveling. I will be in Nigeria by next week. So you could email me and then I will respond to you. And then hopefully I'm planning that we will meet online maybe a week, maybe the Monday before your final. So anyway, I will email you guys to let you know what my plans are in terms of meeting with you online. Yes, but as much as I can, I will send you some additional problems.
Thank you.
Okay. Is there any other question? Okay. If there is no question, I think we have come to the end of our session today. You guys enjoy your turkey. Do not eat too much turkey. And if I don't see some of you before Christmas, also enjoy your holiday. So in the meantime, enjoy the rest of the evening. And by tomorrow, I will post this material in YouTube and also in your Blackboard page. Okay, so thank you for coming today, and I will see you in a few weeks online. So until then, I will say so long. I'm going to stay around for another 5 minutes for those of you who may want to ask me questions offline. Okay?